All right, so today we are looking at area between curves. So we have a couple of functions, call them F and G. Here's one, here's the other. And we want to know the area between those curves between A and B. And then what we are looking for is this area in here. So what we do is the following. So, this probably won't look anything like what it is there. So that area that's there would be equal to this area,
Especially up at the right.
minus
Where's that again?
this area.
Playing this guy, playing this guy. I don't know. Maybe not. Actually, he's not playing, Geordie Mack's not playing, and when they're playing full forward, so. Oh. Yeah, should have better shooters.
Should.
You should win. Well, don't you have a bunch of people not playing there?
We have Logan out, nothing throughout.
All right, so if we want the area in between, if we work out all the area under the higher one, the orange one, and then take away the area under the lower one, the green one, that will give us the area. So in terms of our integrals, we have then that the area would be the integral from A to B of the upper one, which is f x dx, minus A to B, the area under the lower one, which is g. Now, we can also put those two things together as those integrals, because the limits on the top of our integrals are the same. We can then put it together. But we can only put it together like that if these limits here, the upper and the lower, are the same. If they're different, then you can't put them together. But in this particular case, when we're looking at area between curves, these numbers are always going to be the same. Wait till you've got that, because I want to rub it off.
Yeah, after when.
Anyway, this is of course all on the YouTube channel and the website, and you'll be pleased to know that due to your amazing efforts, I've got 4 new subscribers in the last week. At this rate, I'll be 1,000 before I reach.
You need a manager, Mr.
I do. I know, it's starting to get too much for me.
Jen can be your editor. Just 'cause you put-
Almost done, Mr. Senator, almost done.
Almost?
You
Good.
can rub off the two graphs, I just need to do the exam.
Rub off the graph side, it's good, then I can write the exam.
And also the other way, same way.
Alright, so this says calculate the area enclosed by the curves with equations y equals x squared plus 1 and y equals 4 minus x squared, and the lines x equals minus 1 and x equals 1. So we can get a little bit of an idea of what it's talking about. Let's just do a rough sketch. So x squared plus 1 is a parabola, and its turning point is at 1, and nothing else has happened. It's just been shifted up 1. So we've got that there. And 4 minus x squared is also a parabola, yep, and it has been flipped and also moved up 4. So it goes like that. So x equals minus 1 is there, x equals 1 is here, and so if we follow those up, what we're after is that area in there. Alright, so it's always the upper one minus the lower one. So in this case our area will be between minus 1 and 1. The upper one is x squared plus 1. And the lower one is, no it's not, the upper one is 4 minus x squared. And the lower one is x squared plus 1. Alright, so you can do it like that and have it separate, or you put it together, whichever you liked. You put it together, it's 4 minus x squared, take x squared plus 1, and 4 minus x squared, take x squared plus 1 ends up being what? 4 minus 1 is minus x squared minus another x squared is minus how many? Minus 2. Alright, then we use the fundamental theorem of calculus. So when we anti-differentiate 3 we get,
You get 3x.
and when we anti-differentiate 2x squared we get.
To the 3 cubed.
Between 1 and minus 1. We now stick in those numbers. So 3 times 1 minus 2 times 1 cubed over 3. From that we're going to subtract 3 times negative 1 minus 2 times negative 1 cubed over 3. And when you do all of that, you get 14 over 3. So there's steps in here I've left out. There's steps in there between there and there I've left out.
Okay.
There's someone desperately wants me to do. All right. One more example. Not an example, just something to point out to you. Can I rub that off?
Leave up from square brackets 3x minus 2x 3.
You just leave the whole equation.
All right, so the other day when we were looking at area under the graph, and when the graph went underneath the axis, we had to split it up. And so with these, sometimes you might need to split it up also. I say, for example, you've got something like that, and something like that. And we're after this area in here. Then in this part the green one's on top, but in this part the orange one's on top. So if you're wanting to know between the area between A and B,
You need to make a C.
we need to make a C.
Okay.
Yeah.
Looking more and more like DNA.
So we need to know,
Yeah, so I said.
we need to know where that's going to intersect. So we need to know that point, and then we need to do it in 2 parts. So in this case, our area would be 2 parts. So that's F is the orange, and G is the green. So we need to go from A to C, and from between A and C, G is on top. So we've got to do our G minus our F in that case. And then we need to add the other bit, and the other bit is from C to B, and it excuse me, and C to B, the orange one's on top, so it's Fx minus Gx. Right, so it's just something you need to be aware of. All right, applications. There's a couple of things I need to point out.
So that's it on area.
That's it on the area. Yep.
Still got applications. Some more things to do.
Yeah, we do areas, we don't have to worry about volumes. Those lucky people doing specialist maths do volumes of rotation, which is a lot more fun.
Don't worry, she's not listening.
Just that she has new volumes of rotation, other fancy stuff.
You don't have to.
All right, some applications. So, there's this thing called the average value of a function. Right. If I have a curve like this, for example, and we've got between this interval between A and B, all right, so there's this area in here. Now, because of this curve, there's a bit of area up. This is where the average value is. It's a bit weird. So the average value is about, if we create a rectangle, so this green rectangle, where this green rectangle's area is the same as the area underneath the curve. So, you know, these two bits, doesn't look like it in my diagram, but it's because I'm a bad drawer. These two bits of area would be the same. So we've got this rectangle, green rectangle, which is the same area as the area under the graph. Then this average value, what the average value is it's actually this length on the rectangle. So we know that one is the interval A to B, but this length of the rectangle is the average value. And so I better just write that. So the area under the curve is equal to the area of the rectangle. All right, so So the area under the curve, of course, would be, and our function's f. So the area under the curve is the integral from a to b of fx dx. The area of the rectangle is length by width. Now, the length between A and B, the length is
B minus A.
B minus A, correct? And the width is this thing that we call the average value.
So just rearrange the equation.
Very good. We just rearranged the equation. So that's still the integral from a to b of fx dx. So when we rearrange that equation, we find that the average value is equal to 1 over b minus a times the integral from a to b of fx dx. Right, so that is the average value, and they have sometime in the last 3 or 4 years asked about the average value of functions.
What's up with it being smaller under the first one?
When you,
With the calculus with the B and A, is that supposed to be in the other one?
where am I?
I
Looking.
think he's just talking
Oh,
about.
he just did it small.
It's just,
He's
yeah, it should.
second.
Oh, this here? Oh, yeah, I just squeezed it in, that's all. It's got no significance that it's smaller other than that.
Yeah.
All right. Better do an example. All right, just a straightforward one. Average value of fx equals x squared for the interval 0 to 2. So when we look at this here, our average value says it's 1 on b minus a. So b minus a, 2 minus 0 in this case, 0 to 2 of x squared dx. And you differentiate x squared and you get x cubed over 3, yeah. 0 to 2, so that's going to be a half of 2 cubed on 3 minus 0 cubed on 3. And what's in the brackets there is 8/3, I believe. And so 4/3 is our average value. All right, one other thing, and I'm just going to point out the definitions here with this, and then that'll be it. So what this excuse me, what this 4/3 means is if we've got x squared here and 2, that this area here would be the same area as a rectangle which is 2 by 4/3. So those areas would be the same. So what this here is it's finding that side there. Excuse me. This 2 here relates to that one. Yes, Glenn.
So from average value, the first, like when you first, like the first transformation of your equation, why is there a squared outside the square brackets?
Where?
Between 2 and 0.
Oh, okay. And is it
2. Yeah.
There's a zero.
Yeah, it's not a squared,
The
it's
0 is on the 3.
it's an x equals 2. That's what it is, yeah. Anything else? All right.
Oh no.
Sorry, Glenn.
So good.
All right, it's just some definitions. Motion in a straight line. So some definitions. So x is position. Velocity. Yeah, is defined as the rate of change in position. So that's dx dt. And acceleration is the rate of change in velocity, so dv dt. And of course, these we've done. Of course, we can go back the other way as well. So from these, we get that if you anti-differentiate the velocity one, you get position.
Time to wake up, Eliza.
So if we anti-differentiate this one, we'll get position, and the acceleration one, if we anti-differentiate that, we will, if we, the acceleration one, if we anti-differentiate, we'll get the velocity. And you'll be given some equation. Now, the average value has an application with this. So the average value, we can work out the average velocity across a time interval. All right, so also using the average value, the average velocity
Just like,
between time 1 and time 2, whatever they are. So the average velocity would be 1 over the difference in those times, so t2 minus t1, multiplied by the integral from t1 to t2 of v of t dt. All right. All right, so for motion, I'll just leave that with you. I'm not going to do an example. I've already done some stuff with that. And it's all. So you're just going to get an equation which has t in it. So it could be, you know, t squared minus 4 or something like that, and you deal with that. Same way as you do with all the other stuff. All right, that's it for calculus.